For our project, we decided to investigate the wave speed of a battle rope. Specifically, we are exploring the relationship between the wave speed and the driving frequency of the waves that are produced during an exercise with a battle rope. In the video, we're beginning with a lower driving frequency for the waves in the battle rope, and then partway through the video, we increase the driving frequency. When put into the video analysis, we looked at both the low frequency driving force and the high frequency driving force. For the low frequency, when comparing the time and position of a point on the rope, when we did the best line fit on the graph, we got a velocity or wave speed of approximately 9.157 meters per second. When looking at the high frequency driving force for our time versus position, when we did our line of best fit, it was going to be a velocity of 9.469 meters per second, which is not exactly the same as our low frequency, but is very close to it. So some important definitions to know. The first is what a traveling wave is. It's just an organized disturbance that travels at a well-defined wave speed. A wave speed is just obviously the speed or velocity that the wave is going to travel through the medium. In this case, it's going to be the rope. Linear density, which is the mass to length ratio of an object. We calculated the linear density for the rope within this experiment. The frequency is just simply the number of cycles per second for a wave. And the medium is the substance through which the wave moves. So a few important equations to consider. As I mentioned earlier, the linear density is just the mass of an object divided by its length. Frequency is going to be the velocity divided by the wavelength. And the wave speed, which is the velocity, is actually going to be equal to the square root of the tension of the rope divided by the linear density. So the important calculations done for this experiment is finding the linear density of the rope. The rope weighed about 6.9 kilograms, and it was a length of around 4.572 meters, which gave us 1.5092 kilograms per meter for the linear density. The other important thing that we calculated was the tension of the rope, since we had the velocity and the linear density. So for low frequency, this is the velocity that we calculated using the video analysis. And by using a little bit of algebra, we were able to discover that the tension of the rope here is 126.5 newtons. For the higher frequency, it is 9.469 for the velocity, and so we were just using the same methods we did for the low frequency. We were able to determine that it is 135.3 newtons for the tension of the rope. So the big conclusion that we made is wave speed is a property of the medium. So it's going to be a constant variable, and that will only change depending on how the medium changes. So in our experiment, the medium was a battle rope, and in order to change the wave speed, either the tension of the rope would have had to be increased or decreased, or the linear density of the rope would have to change. So as we could see earlier with our calculations, with the slight difference in the tension from the rope when we were calculating a lower frequency versus a higher frequency is what resulted in that slightly different velocity that we established. Though it is assumed that a change in frequency may seem like it would affect the wave speed, it actually only changes the wavelength since the two values have an inverse relationship, so the wave speed is going to remain constant.